All right, folks, here's a classic exponential growth word problem. You should be able to do this, but I'm going to walk you through it. So it says you deposit $7,500 in an account that yields means gains. When you yield something, you're getting something, okay? Yields 11.3% interest per year, compounded monthly. How much will you have after 41 years? Well, to start with, this problem doesn't have the word continuously in it, and you see the word compound, the words compounded monthly. Those are very clearly now this is discrete growth. And it's growth because it's yielding. And also when you deposit money in an account and you're getting interest, that means your money is going up. It's gaining in value. So this is a discrete growth problem. So we're going to put in P, our starting value, which is 7,500. So we're going to put 7,500, parenthesis, right? 1 plus, R is the percentage rate, so 11.3%, that's 0.113. So 0.113 over N. How many times a year? Well, it's monthly. How many times does monthly happen in a year? 12 times. So divided by 12 to the power of N, which we just determined is 12, times T. How many years? After 41 years, times 41. So now we're going to simplify this. We're going to do 1 plus 0.113 divided by 12 is 1.009417. I'm rounding on that last number. So what we have here is 7,500 times 1.009417. The more zeros you have here, the farther out you want to go. Okay, so if you got a couple zeros here, you want to go to maybe 4 decimal places after you're done putting zeros in. To the power of, what's 12 times 41? Well, that's 492. And now this we can just put in the calculator. I'll do this. Actually, let me show you how you can put this all in one shot in the calculator. Okay, so there's our, okay, let's see here, where's it? There's our, okay. There is our formula. Right there, we're going to key that in here. All right, so we're going to put in 7,500 parenthesis 1.009417. Okay, I don't know if you see that. Close the parenthesis to the power of, is it 492? 492. So we're putting the whole thing in one shot, and we press enter, and the calculator will do it in the correct order. And we get, wow, that's a big number. And we get 750,750.90. So this is money, right? So $7,500 over 41 years at 11.3% interest, $754,750. Now that's real deal. You could actually do that. If you're 17 years old or 18 years old and you put $7,500 into a mutual fund, and that mutual fund yields about 11% interest, in 41 years you'll have about $750,000 that you can then go spend when you're retired. You'll be what, like 58 years old or 57 years old, something like that. And you'll have all that. That's one time you put that money in. You didn't keep putting that money in. That one time, that one amount of money became that after 40 years. So I recommend, if you want to do some investing yourself. And you didn't have to put this, you didn't have to watch this in the stock market. Someone else put it in the stock market for you and they watched it grow. You just waited for it to grow. And now here you are 57 years old, and you can go buy a boat or buy a nice house or something that you can retire in, okay? All right, so that's that. All right, let's do another example. All right, here's another situation. You buy a car for $30,000 that depreciates. See this word depreciate? That means loses value. That means the value is going down. That means the value is decaying. That means it's a decay problem. depreciates by 3.1% per year, realized semi-annually. This does not say continuously, it says semi-annually. That means twice per year. That means that N is equal to 2. And the rate R is 0.0371. R is, so we turn the percentage into a decimal. Here's the N, and we're going to put a minus in front of that, right? Because that's in the formula. So let's go ahead and use our formula. P, starting value. Well, when you bought the car, it was $30,000. So we'll put in 30,000, then a parenthesis, then a 1, minus, because it's losing value, R is 0.0371. So 0.0371 over N. How many times per year? Twice a year, semi-annually. That's 2. To the power of N, which we just said was 2, times T. After how many years? After 8 years. So 2 times 8. So let's simplify this a little bit. We'll go 1 minus 0.0371 divided by 2. Okay, so we have 30,000 times 0.98145. Remember what we said? That when it decays, when the value goes down, this number here will be less than 1. 2 times 8, that's 16 to the power of 16. Okay? All right, so let's go to the calculator. We'll go 30,000. See here. 30,000, parenthesis, 0.98145. Close the parenthesis. To the power of 16. Press enter. See what we get here. All right, we get 22,233. 22,233.72. So that car 8 years ago when you bought it was worth $30,000. Now 8 years later, it's only worth $22,233. Still, that's pretty good. That must be a Honda or a Toyota or something. They keep their value for a long time. All right, so there we go. There's that situation. Let's do another one. Let's just do 2 more, but we'll do another one. All right, here we have a sad situation. We've got a population of deer that is dying because of a disease. So we get this disease is special to this, species of deer. There were 180,000 deer, and they are dying. I didn't quite word it correctly, but they're dying continuously at a rate of 5.63% per year. How many deer will there be after 4 years? Okay. Oh dear, this is a terrible situation. Oh dear. All right, I know it's terrible, but I haven't told a joke in a while. Okay, all right, so let's see here. Dying continuously. Continuously means we have to have an E. Dying means there's fewer of them, which means we're going to have the negative R. So this is our formula, continuous decay. So P, starting value. Well, there were 180,000 deer, so we're going to put 180,000. Then E, right? Then times E to the power of negative R. Well, R is the percentage. That's 0.0563. Move the decimal point over 2 places, right? Or divide by 100. 5.63 divided by 100 is 0.0563. So to the power of negative 0.0563 times time. How many years? After 4 years. So we'll put a 4 here. All right, let's simplify this. Negative 0.0563 times 4 is negative 0.2252. So we've got 180,000 times E to the power of negative 0.2252. Let's put that in the calculator. 180,000 times, hit second ln to get the E, negative 0.2252, and press enter. And it says there's going to be 140, after 4 years, 143,704. Now there is a point 1757, 1757. And we could put that on there, and that's how many deer. But remember, deer come in whole numbers. So we could just leave that off or just round it and say 143,704 deer, okay, after 4 years of dying from this disease. So it's pretty tragic. All right, let's do one more situation. All right, we've got the situation. We got the population of a city. It doesn't matter what city it is. There's some city out there, and its population is 2.3 million people and growing continuously at the rate of 1.93% per year. What will the city's population be after 9 more years? All right, well, we've got continuous growth, which means the continuous growth formula, which is the PERT formula, P times E to the power of R times T. All right, so what is P? P is the starting value. Currently, there are 2.3 million people in the city. So we're just going to put 2.3, and we'll put the million on later. 2.3 E to the power of R. R is the rate. Well, what is 1.93% as a decimal? Well, if you divide 1.93 by 100, you get 0.0193. So to the power of 0.0193 times time. What will the population be after 9 more years? So times 9. So let's go to our calculator. We're going to simplify this. 0.0193 times 9 is 0.1737. So we're going to put 2.3 e to the power of 0.1737. Just got to put it in the calculator now. So you got here 2.3 second ln gives me the e to the power of 0.1737. All right, press enter. And we get 2.736. Let's stop there. 2.736. And then we'll just put the word million on there. Million people, I guess, if you want to. 2.736. And this is how we can calculate what the population of a city is going to be 9 years down the road. Now, it's not going to be perfect. The growth rate could change in the next 9 years. And there could be a major thing where 500,000 people decide that they hate it in the city and they wind up moving out. Or there could be a new fad, everybody gets excited about the city and an extra million people move in. This growth rate, mostly, not entirely, but this growth rate has a little bit to do with people moving in, but a lot of it has to do with these 2.3 million people procreating and multiplying and having kids and that sort of thing, okay? So, and usually these growth rates in the cities, they include the death rate. They take the birth rate plus the rate at which people move in, they subtract away the rate at which people die, and then they ball it all into just one city growth rate, which is that percentage. Well, for this example, that's what it is, okay? All right, so that's it. That's how you use these 4 formulas. And now your worksheets, you're going to have to be able to use these formulas proficiently. And once you're good at this, now see, I need you to be good at this. I need you to be good at plugging in and solving, because eventually what we're going to do is I'm going to stop giving you all these numbers. I'm going to give you the answer, and I'm going to give you the beginning, and I'm going to give you the time, and I need you you're going to have to calculate the rate of growth. That's going to be your job. So let's say you're a city planner and you have numbers, a beginning number and an ending number, and you take the time and you have to figure out the rate at which the population is growing. And then you're the one who publishes that, and everybody's like, oh, wow, look at that number that person posted, okay? All right, so you're going to have to learn how to do that. So work on these problems, and I'll see you in class.